Imagine a typical university statistics class. Let's call the professor Dr. Zeppo. Over the years, Dr. Zeppo has graded hundreds of students on a strict curve, giving us a massive historical baseline to look at. This chart shows the historical distribution of grades. The average score sits in the center at exactly 67.5, with a standard deviation of 9.5. Now watch what happens when we isolate 20 psychology students. Their average score lands up here at 72.3. Curious, we have a gap. But what does that gap actually mean? Are psychology students naturally better at statistics? Or did Dr. Zeppo just happen to get a cluster of lucky test takers this semester? To separate pure luck from a real academic trend, we can't just trust our gut. We have to run these numbers through a statistical lie detector known as the one-sample z-test. Human intuition is terrible at judging whether a cluster of data is a meaningful anomaly or just random noise. We need strict mathematical rules to tell us the truth. Though, as we will see, the specific rules of the z-test come with a rather hidden cost. Every statistical test starts by drawing a line in the sand. Before we look at any more data, we have to define two opposing realities. The first is the null hypothesis. This is the assumption that the psychology students are perfectly average and that their slightly higher score is just random noise. Under this reality, their true mean is exactly 67.5. The second is the alternative hypothesis. This asserts that the psychology students are genuinely, measurably different from the rest of the class. To figure out which reality we live in, we don't just subtract the scores. We have to convert that raw difference into a standardized weight of evidence, which we call a z-score. We take our sample average of 72.3, subtract the population average of 67.5, and divide by the standard error, the standard deviation of 9.5 divided by the square root of 20. The math simplifies to a single number, a z-score of 2.26. By standardizing the score, we strip away the specific grading scale of Dr. Zeppo's class. We now have an objective measurement of how far our sample has drifted from the historical average. But a z-score of 2.26 doesn't mean anything unless we have a universal ruler to measure it against. This standard normal distribution measures random chance, centered at 0. Setting a 5% alpha level creates rejection regions on the extreme margins. If a score lands here, it's not just luck. Our z-score of 2.26 lands firmly inside that upper rejection region. Translating that physical spot into a probability gives us a p-value of roughly 0.023. That means there is only a 2.3% chance that an average group of students would score this high by pure luck. Because 2.3% is smaller than our 5% threshold, we officially reject the null hypothesis. The math confirms it. The psychology students are scoring higher than the rest of the class. So the math works perfectly. But if you step out of the classroom and into a real data science lab, you will almost never see this test used. It is, for all practical purposes, a theoretical fiction. To make that elegant formula work in Act 2, we had to rely on a very specific piece of information. We assumed we knew the exact standard deviation, the precise spread, of the entire historical population. Here's the problem. In the real world, you cannot calculate the true standard deviation of an entire population without also knowing its true mean. And if you already know the population mean, you don't need to run a hypothesis test. You are left with a paradox. The one-sample z-test requires you to know a population parameter that you are completely ignorant about. If the test contradicts the reality of data collection, why do we bother learning it? Why is it universally taught in every introductory statistics course? Because the z-test is the spherical cow of statistics. It is a perfectly frictionless model designed to teach you the philosophy of hypothesis testing without dragging you into the mathematical mud of real data. By walking through this theoretical exercise, you learn how to weigh evidence. You learn the universal language of standard errors, p-values, and alpha levels in a controlled environment. This framework provides the scaffolding for almost every decision that follows. By mastering this logic, you've prepared yourself for the t-test, the workhorse used to validate medical trials, test engineering tolerances, and verify modern scientific research.